of our interesting collision problem, but this time it's inelastic collision. Let's see what happens. All right, same as before, ball little m hits ball big M with a velocity v. Now the collision is inelastic. The two move apart at equal and opposite velocity. Okay, this in the positive direction and that in the negative direction. Equal and opposite velocity. Question is, how can this happen? Let's analyze it. First, from point of view of momentum. The momentum analysis will be giving us exactly the same solution or result as before. Before collision, after collision. Before collision, momentum is mv, all right? And after collision, well, momentum a vector, so I have to add this and subtract that. So that's big M v prime minus little m v prime. That's v prime big M minus little m. Let's introduce that variable again. Ratio of the masses. mv, let's divide by m here. I get v prime 1 minus, u minus 1. As before, okay. All right, now the energy analysis. Okay, energy before has to be equal to the energy after. Okay, energy before, what's that? Well, it's the kinetic energy here. Energy after is what? Well, it's the kinetic energy of this plus kinetic energy of that plus whatever is lost due to the inelastic collision, like the heat. So 1/2 mv squared, that's 1/2 mv prime squared plus 1/2 big M v prime squared plus q. Q is the heat or energy dissipated in this collision, you see? All right, so we need to kind of be more specific about Q. Let's say it's some fraction times the initial energy. What is this initial energy? It's the kinetic energy of ball little m, all right? So this is F times 1/2 mv squared. Total energy at the beginning of the problem was this. We want to say that Q, how much was lost due to inelastic collision, is some fraction like so. So when F approaches 1, then it's 100% inelastic. And if F approaches 0, then we have 100% elastic case. Nothing is lost. We can reverse this by defining a different variable, 1 minus F, call it eta, efficiency. And when eta approaches 1, then I have 100% elastic case. Okay, now why do I introduce this new variable? You'll see in a minute, okay, you'll understand soon. All right, let's continue the energy analysis over here. Okay, so we have 1/2 mv squared is 1/2 mv prime squared plus 1/2 mv prime squared plus q. Let's bring the q to the other side. I have 1/2 mv squared minus q is 1/2 mv prime squared plus 1/2 big M v prime squared. Okay, first of all, let's take care of this q. This q, as we said before, is F times the initial kinetic energy. So I can factor this out. 1 minus F, 1/2 mv squared is 1/2 m v prime squared plus 1/2 big M v prime squared. Great, that's efficiency. Let's cut this out. This is going to become u when I divide by little m. I have efficiency v squared is equal to v prime squared plus u v prime squared. Let's factor out v prime. V prime squared u plus 1. Beautiful. Now this, I can substitute what I did with the momentum equation. Same technique as last time in the last video, same technique. So let's square this and substitute in here. I have eta v prime squared u minus 1 squared is v prime squared u plus 1. let's cancel this out. I have eta u minus 1 squared. Very beautiful. Isn't that nice? It is the same as the equation we got last time, except I have eta in front. And if I go eta is 1, it's elastic. And I get the same equation as last time. Same as before. Okay, that's interesting. Now, what happens if eta go to 0? So the collision is 100% inelastic. Now here, I'm telling you, here is something that your intuition is going to help you with. Think about this. 100% inelastic collision. All of this kinetic energy is lost. What's going to happen next? What are the conditions for this to happen? I think your intuition will help you here. You think about it, but I'm going to do it here. You can pause the video, think about it, and then check, see if your intuition was right. All right. When eta is 0, let's say eta go to 0. So eta, let's take this and bring it over here. Eta is u plus 1 over u minus 1 squared. Now this can go to 0. When does this go to 0? This can go to 0 when you go to infinity. You see? When you go to infinity, this becomes really big. Second order and first order. I just divide everything by u. I get infinitesimals and so on. And this 0 goes to 0. What does this mean? It means that big M over M go to infinity. So M must be infinitely heavy. You see? So I end up with a case like this. Tiny little mass M with velocity V, and I have infinitely big mass. And the collision 100% inelastic. So the infinitely big mass absorbs everything. The little particle M sticks to the big mass. What is the rebound velocity here? And what is the velocity here? It should be equal. Okay, let me draw them as equal length vectors. V prime here, V prime, they must be equal. Well, it's going to be 0 meters per second, and here 0 meters per second. Yes, they are equal. They are equal. They are 0. How do we know they're 0? Well, let's go here. Put this in. V prime equals V over u minus 1. U is really big. So this is V over infinity. This is 0. V prime is 0. The limit is 0 as u goes to infinity. So we did it. We understand the inelastic case. It's very amazing and very beautiful thanks to this incredibly beautiful formula. Okay, that's really nice. I really enjoyed this. I hope you did. If you like this video, click like, subscribe. We'll do more cool physics problems.